Welcome to our presentation on Bioclimatic Design Climate. I'm Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. In this video, we will discuss how climate conditions influence bioclimate design strategies in achieving energy savings and user comfort. Key reference books are Design with Climate by Victor Olgai, which emphasizes climate-responsive design. Lessons from Modernism explores bioclimatic strategies from 1925 to 1970. We discussed the net zero design approach in the Zero Design videos. The net zero energy approach on the left consists of bioclimatic design, energy efficient systems, and renewable energy integration. The design goal is to reduce energy use through bioclimatic strategies and energy efficient building service systems. This video focuses on bioclimatic design. Then, the on-site renewable energy system is integrated to support building operations. The net zero carbon approach on the right requires additional strategies beyond the net zero energy approach. Additional strategies include the use of renewable bio-based construction materials and the integration of vegetative systems, both of which offset carbon emissions from the building overall. The final performance goal is to design buildings that achieve both net zero energy and net zero carbon. For more information, refer to the additional videos indicated in the slide. 1. Bioclimatic design is a fundamental step toward net zero building design strategies that utilize climate and site resources to create a healthy, energy-efficient built environment. 2. Bioclimatic design enhances occupant comfort, health, and well-being through natural ventilation, shading, daylighting, and moisture control. 3. Bioclimatic design minimizes the use of active building systems and reduces energy consumption in heating, cooling, ventilation, and lighting energy. 4. Bioclimatic design preserves natural resources while protecting surrounding ecosystems such as bodies of water, vegetation, and natural habitats. The effective bioclimatic design starts with understanding the key climate factors. 4 fundamental climate factors include temperature, solar radiation, humidity, and air movement. These factors have an impact on the building configuration, system selection, and the occupant's comfort. For example, temperature swings and extreme temperature influence heating or cooling capacity and building enclosure specifications. Solar radiation and air movement affect facade designs such as windows, shading devices, and solar collectors. Humidity impact ventilation strategy and material selection. Bioclimatic design balances all climate factors to transform local climate challenges into opportunities for comfort and efficiency. Understanding climatic characteristics provides important contextual information for bioclimatic design. The map on this slide shows how climatic zones are distributed geographically according to temperatures, humidity, and vegetation types that these climates support. This classification assists designers in understanding the general climatic characteristics of the location of a project. For instance, understanding a site's location as a humid subtropical zone rather than a dry savanna guides our approaches toward whether we'll be dealing more with the need for cooling and dehumidification or more with shading and water conservation efforts. In other words, climate classification determines the broad environmental circumstances we must respond to and that need to inform the design approach. Referenced by Köppen Climate, the U.S. established the ASHRAE climate zones to provide environmental design parameters. ASHRAE categorizes regions into climate zone 1 through zone 8, from very hot to very cold based on temperature. Humidity criteria use humid, A, and dry, B. For example, 3A is warm humid, 3B is warm dry, and 3C is warm marine. These climate zones help prioritize primary performance goals such as cooling, heating, humidification, or dehumidification, all of which contribute to energy savings and comfort levels. Now let's consider human thermal comfort, essentially how our bodies react to different climatic conditions through evaporation, conduction, convection, and radiation. These thermal regulation processes and indices for thermal comfort draw on knowledge from medical science, biology, environmental technology, and meteorology to quantify comfort. This thermal experience and response eventually drive the operation of active building systems. When buildings are designed to provide comfortable experience from the outset, the reliance on HVAC will be minimized because most of the day and year offer a pleasant environment that keeps occupants in comfortable thermal equilibrium. This slide shows the psychrometric chart, an essential tool for analyzing air conditions and strategizing passive comfort solutions. The graph on the left is an earlier, simpler version, accounting for temperature on the vertical axis and percent relative humidity, %RH, on the horizontal axis. The graph on the right is an ASHRAE version, which, on the other hand, accounts for 4 environmental factors: their operative temperature on the horizontal axis, dew point temperature and humidity ratio on the vertical axes, and %RH indicated by curved lines. The areas highlighted with hatched zones indicate acceptable ranges of operative temperature and %RH for people in summer and winter during primarily sedentary activity. For example, when the temperature is 26 degrees Celsius with 30% RH in summer, this will likely feel comfortable, even though the operative temperature is higher than the typical summer set point. This helps us select natural conditioning strategies during the bioclimatic design process before activating mechanical air conditioning. The central comfort zone, highlighted with green, roughly 20 to 26 degrees Celsius in temperature and 20 to 80% relative humidity, represents conditions that are naturally comfortable indoors. This comfort zone is overlaid with the Givoni bioclimatic chart. The highlighted point at 23 degrees Celsius and 40% RH lies inside this zone, meaning no active heating or cooling is needed. Surrounding the comfort zone are regions for various bioclimatic design strategies. Just above it is a natural ventilation zone, indicating that if it's a bit warmer, increased air movement such as breezes or fans can restore comfort. Further right toward hotter, drier conditions lie the evaporative cooling zone, where adding moisture such as evaporative cooling lowers the temperature into the comfort range. On the cool left side, a passive heating zone is shown, meaning conditions below 20 degrees Celsius require adding heat, for example, passive solar gains, to reach comfort. This psychrometric chart includes a green shaded area representing the ASHRAE 55 2017 comfort zone, the range of temperature humidity conditions where typical occupants feel comfortable. For this scenario, conditions include an airspeed of 0.2 m/s, clothing insulation 1 cilo, metabolic rate 1 met, and mean radiant temperature 20 degrees Celsius. The reference data point at 23 degrees Celsius dry bulb and 40% relative humidity lies near this green zone but slightly outside it, as indicated by the red not compliant warning on the top left corner. This means the condition is marginally too cool according to the standards criteria. More specifically, under these conditions, the predicted mean vote, PMV, indicates a slightly cool thermal sensation. In other words, the average person would feel just a bit cooler than neutral. The predicted percentage of dissatisfied, PPD, is around 5.8%, meaning roughly 94% of occupants would still find this environment acceptable. A slight increase in the operative temperature by about 1 degree Celsius would bring this point into the green comfort zone, achieving compliance with the standard. The diagram on the left presents bioclimatic design principles for keeping buildings comfortable in hot, humid conditions. Building spaces and site conditions should be designed in a way that encourages cross-ventilation, natural shading, and moisture control in hot and humid environments. On the right, there are 4 bioclimatic design strategies for humidity, temperature, radiation, and air movement. Moisture control is typically handled through vapor barriers and ventilation, in addition to active dehumidification systems. Heat balance can be achieved with good thermal insulation and heat wave protection. Daylighting penetration is maximized through penetration area, orientations, and daylighting systems like skylights, windows, and clerestories. Solar radiation protection and penetration can be addressed through building mass, facade treatment, and site design. Air movement around and inside the building helps with natural ventilation and cooling. All these bioclimatic strategies reduce energy use, promote occupant health and well-being, and improve material longevity. Before we begin designing any sustainable or net zero buildings, we perform a climate analysis of the site, study the local climate data in detail, and how the building, site, and climates interact to shape the design in response to such environmental forces. Temperature swings throughout the day and year, sunpath data with solar intensity each season, prevailing winds, humidity levels, and precipitation patterns are essential for bioclimatic design. Analyzing these factors allows us to identify design opportunities and challenges. This slide shows a real-world project that incorporates bioclimatic design strategies. The headquarters of the Chesapeake Bay Foundation opened in 2001 and received the world's first LEED Platinum. The building shape and the strategic placement of clerestory windows capture prevailing offshore winds for natural ventilation during mild seasons. The clerestory windows support not only cross ventilation but also daylight illumination. The sloped roof from the clerestory collects rainwater into the cisterns located on the north facade. The overhangs provide semi-outdoor space and filter harsh sunlight before it penetrates the inside. The use of recycled and locally sourced materials contributes to carbon reduction. The landscape features native, flood-resistant plant species that require minimal irrigation instead of traditional high-maintenance vegetation. Bioclimatic design is accomplished through the consideration of site, climate, and building to create a sustainable, climate-responsive, and site-sensitive built environment. From an energy and climate perspective, the building's envelope is highly insulated and airtight in the winter. Operable apertures and vented cupola can open on cooler summer evenings to flush heat and natural night purge ventilation. The architects shaped the building to provide the ability to breathe and stay cool during hot and humid summers with minimal mechanical aid, and to capture heat during the winter to stay warm. This headquarters continues to demonstrate that mindful, climate-friendly construction translates to lower energy use. It operates well below the energy consumption benchmarks set for buildings of its size. It has become a successful example of the integration of climate factors, including design considerations, site placement, shading, and ventilation, marking a sustainable architecture achievement. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Let's work together towards a sustainable future.